Good day, girls. In this lesson, we will be learning about images formed by converging lenses and how we apply them to the human eye. So when it comes to a converging lens, the image that is formed depends greatly on where the object is located. So when the object is very distant, in other words, beyond 2f, we will get a real image that is inverted, smaller than the object, and is located between f and 2f on the opposite side. This is used in the objective lens of a telescope. When the object is located exactly at 2f, it is real, inverted, but the same size as the object and also located at 2f. This is used in a photocopier. Why? Because it produces an image that is the same size as the object, hence a photocopy. When the object is in between 2f and f, then we also have a real and an inverted image, but it is larger than the object and beyond 2f, so it gets further away. We have two devices that use this particular location, namely a projector and a microscope, because we want the image to be bigger than the object itself. When the object is at f, then we say no image is produced, but the refracted rays are parallel. Even though no image is produced, we still have a use for it. It is in a police spotlight. You may have seen one in probably the Batman movies, the bat light that they project on the clouds, right? It's a parallel beam of light. That's a police spotlight. It uses the object right at f. And finally, when the object is in between f and the lens, it is the case where a virtual and upright image is produced, and the image is larger than the object and it is behind the object on the same side of the lens. We have a couple devices that use that, namely a magnifying glass and glasses for farsightedness, also known as hypermetropia. So when it comes to the images formed by a converging lens, there are a couple things that we should notice that are similar for real images. As long as you have a real image, it is always going to be inverted. Now, what may vary is the size of the image and its location. So the further away the object is, then the smaller the image. And the closer you bring the object to the lens, then the bigger and bigger the image becomes. Now, let's look at the image formed by a diverging lens. This is much easier because no matter where you place the object in a diverging lens, the image will always be the same, and that is, it's always going to be a virtual image and it's going to be upright. It's going to be smaller than the object and it's going to be between the object and the lens. This is used in glasses to correct short-sightedness, also known as myopia. So let's take a second to compare the virtual image produced by a converging lens and that by a diverging lens. What do they have in common? What is different? Well, one thing they have in common is that all virtual images are upright. But what is different between that produced by a converging lens and that produced by a diverging lens? The size. A converging lens produces one that is bigger. A diverging lens produces one that is smaller. The location as well. The converging lens produces one that is further away. The diverging lens produces an image that is closer to the lens. Okay? Those are some good comparisons to remember when looking at the real images and the virtual images. Now, let's take a look at the eye. In biology class, you are going to be looking at the eye more in detail, but this is basically how the eye works. So, an image is formed on the retina of the eye by successive refraction at first the cornea, then the aqueous humor, the lens, and the vitreous humor. So electrical signals then travel along the optic nerve to the brain to be interpreted. Objects at different distances are focused by the ciliary muscles, which change the shape and hence the focal length of the lens, which is a process known as accommodation. The lens is flattened to view near objects. So the ciliary muscles, they release and make the lens fatter to view near objects. To view further objects, they then contract and make the lens thinner. So a normal human eye can accommodate the range of distances from about 25 centimeters, known as the near point, up to as far away as infinity, which is known as the far point. Here's a good little thing for you to try. Take a ruler and you put it in front of your face, right up to it, right? And then what I want you to do is look at 15 centimeters on the ruler. Put your finger right there, remove it, and don't move your finger. Focus on your finger. If your eyes are good, then you should be able to focus on that 15 centimeters without having any strain on your eye. The older you get, then it goes away further to about 25, 30, 35, 40 centimeters. Okay? What are some defects of the eye? Well, being unable to view far objects or near objects in focus is what we call lack of accommodation or presbyopia. And it affects us all as we get older. Why does it occur? Well, because the ciliary muscles gradually become less able to change the shape of the lens enough to focus on objects which are either far away or very close. And that happens because we like to strain our eyes on devices late at night, watching TV, watching our phones, watching our tablets. That is one way, the most common way that we strain our eyes. If we also view things in very low light conditions when our eyes need more light, or the opposite as well, when we look at things that are too bright, when we should view it in low light conditions. In particular, there is myopia, also known as short-sightedness. This occurs when a person can see objects nearly, but they cannot see things all the way to infinity. Their far point is closer than infinity. The image of a distant object is formed in front of the retina because the eyeball is either too long or because the eye lens cannot be made thin enough. Hypermetropia, on the other hand, is also known as long-sightedness. A long-sighted person sees distant objects clearly, but the near point is beyond 25 centimeters. The image of a near object is focused behind the retina because the eyeball is either too short or because the eye lens cannot be made thick enough. So as we see here, the lens within your actual eye is too fat. In other words, it is too strong. So it focuses before it reaches the retina, before it reaches the back of the eye. Or it could just be that your eye is too long. And yes, girls, I know you're having a laugh, right? There are actually long eye people out there, right? Somebody's eye can actually be too long. The opposite is hypermetropia, where the lens could be too weak. In other words, it is too thin. It cannot be made fat enough. And so it doesn't bring the rays to a focus in a short enough distance. The rays focus behind the eye in theory, right? It's a virtual image. Or it could actually be that the person's eye is too short. These are corrected by using lenses. So farsightedness is corrected by using a converging lens. Okay? Farsightedness without a converging lens would have the image being formed behind the lens. Since the converging lens brings these light rays closer together, then it brings it about just enough so that it forms right on the retina. Nearsightedness then is corrected using the opposite, using a diverging lens. Since the lens of the person's eye is too strong and it converges before it reaches the retina, the diverging lens then spreads it out just enough for them to then be converging correctly at the point on the retina. And that is all for the types of devices that use lenses and the human eye.